Hi, everyone. In this video, I will be talking about exploratory factor analysis using Stata. Now, exploratory factor analysis is basically a technique that is designed to allow you to explore the interrelationships among a set of measured or observed variables. And the idea is to try to discern whether there are some underlying factors that account for those relationships. So as you can see on your screen right here, I've just got a couple of models, exploratory factor analysis models. It's basically a two-factor model. And these are the models that we will ultimately be coming up with as we go through this particular video demonstration. But if you look at it, this is kind of using diagramming that if you're familiar with structural equation modeling, you'll notice that the boxes represent the measured or observed variables in the data set. The ovals on the right, where it says spatial and verbal, those represent latent variables or underlying variables, with the idea that those variables may be accounting for the relationships among the observed variables. And you'll see that we have these arrows pointing from those latent variables to the measured variables, just kind of representing, again, that idea that the variation in those observed variables is reflecting those latent variables. You'll also notice, too, that on the left, you've got these little circles. Those are basically referring to measurement error associated with each variable. And the term that we would use is called uniqueness. So as you can see in both of these models, there is measurement error that is associated with each of the measured or observed variables in our data set. So what we'll be doing is we're going to be taking this set of 6 measured variables and performing the exploratory factor analysis. And so this right here, this actually reflects where we're going to end up at the end of the video. But this is just kind of capturing the general idea behind exploratory factor analysis. So what we do is we take a set of observed or manifest variables. We go through a series of steps to try to determine how many factors might account for the interrelationships among the set of variables. Then once we've made that determination, we essentially perform our main analysis and retain that many factors. And then from that, we try to interpret the factors based on the relationships between those manifest or observed variables and the latent factors. So there's a series of steps that are involved in factor analysis. And so when it comes to carrying out the analysis with any program, but including with Stata, you need to be thinking through these steps. So the way I've got this presentation sort of arranged is to essentially walk you through decision steps and show you the associated procedures using Stata. Now, if you're familiar with a program like SPSS, it has sort of the drop-down menus, and you can kind of just do a few points and clicks, and then you can generate your output kind of all in one step. That's great, but in Stata, a lot of the procedures, a lot of the commands, if you will, are distributed across different modules, if you will. So there's like the main exploratory factor analysis, where you can carry out the main analyses. There's also post-estimation commands, and then there's also other commands that are not necessarily part of the base program, and so you have to import them as a package. And to tell you the truth, some of the things in SPSS, it's also going to be limited in that it's not going to contain everything. So as we go through the video, what I'm going to be doing is I'm going to open up a do file, which is basically kind of a syntax editor, if you will, and then type in the syntax, and I'm going to explain what's going on as we go through. And my recommendation for you, as you're working with Stata, particularly in these cases where there are analyses involving a lot of different procedures and decisions and so forth, is to kind of work on developing a strategy for writing up a do file so that you can you can save it, and then you can use aspects of it in the future. So at any rate, that's how I'm going to be proceeding in this particular video demonstration. So I'm going to go ahead and open up Stata. So here we are, and just kind of taking a quick look at it. The data is actually already imported into Stata. And you can actually download a copy of the data by following the link that's provided underneath the video description. But basically, this is data coming from about 301 7th and 8th grade students. These are basically measures of intellectual ability. This is from the classic Hausinger and Swineford 1939 data set, and it's used quite often in illustrating factor analysis and related procedures. So the variables that we have in our data set are these right here. We have visual perception, cubes, lozenges. Then we have this paragraph completion, sentence completion, and word meaning right here. And just kind of, if we just take a brief look just at the variables themselves, it kind of looks like maybe some of these variables might reflect kind of a verbal ability type of factor, and some of them might reflect more of a spatial ability factor. So, but typically, oftentimes when we go into factor analysis, we may not necessarily have a very clean idea about where things might load. We might have a general idea about which variables might go together, if you will. And that's where exploratory factor analysis really becomes handy, as we can kind of explore the structure of the underlying data, try to identify those factors that account for the interrelationships among our variables. So in our data set, our raw data set, we have 301 cases. And really the first step when it comes to carrying out exploratory factor analysis involves studying the correlations among the variables themselves. So essentially kind of compiling the information into a correlation matrix and then studying aspects of that correlation matrix to determine if it even makes sense to perform an exploratory factor analysis. So as we're thinking through this process, we want to one thing that the thing that we don't want to have happen is we don't want to have a correlation matrix where essentially the variables are uncorrelated with each other or minimally correlated with each other. So essentially, we don't want to have a correlation matrix where the correlations are all around zero. That's not an ideal situation for carrying out an exploratory factor analysis. By the same token, we also don't want to have collinearity among our variables as well. We don't want to have linear dependencies in our correlation matrix that could end up producing sort of problems in terms of our model estimation. So that's kind of the first step in the process. And then once we make that decision, then we kind of, if we decide that it's reasonable to carry out an exploratory factor analysis, then we proceed to the next step, which is to explore possible factor structures. So in other words, to kind of determine how many factors might account for the interrelations among our measured variables. So I'm going to go ahead and open up a do file. I'm going to click up here at the very top. I'll just kind of show you. I will circle it on here. So there's our little link, our little icon to open up our do file. So I'll click on that, and so you can see here's my do file. And what I'm going to do is also I'm going to kind of increase the font size. Well, I guess I can't do it until I actually put something in. So what I'll do is I'm going to start out with that first step of just looking at the correlation matrix to determine, is it even reasonable to carry out the factor analysis? So I'm going to start by typing in PW core and then the names of the variables in my data set. So the names of the variables that I'm going to be subjecting to factor analysis are the visual perception. So I'll type in viz, PERC. We have cubes, we have lozenges, we have para comp right here, we have cent comp right here, and then word mean right here. And I'm going to be using these in the future, so I'm actually going to go ahead and copy these so that I can just paste them in later on as I need them. Then I'll type in a comma, and then I'm going to use the list option right here for list-wise deletion, because when I carry out my factor analysis, it's essentially by default going to use all cases that have all that have observations on all the variables they're being subjected to factor analysis. And so if I leave this off, basically what will happen is it'll use pairwise deletion in order to construct the correlation matrix. And we're going to actually just kind of make the assumption that we're going to be working with the full complete data set. So now what I'll do is I think I can zoom in now. Yes, so I will just kind of go in here and zoom it a bit for you so you can see a little bit more clearly. All right, there we go. So at this point, I can highlight this and I'll click the execute selection button. And so now you can see that I get a correlation matrix. So in this correlation matrix, what we're looking for is evidence that it's reasonable to carry out the factor analysis. And so we are essentially, one of the main things is to look to see if you have correlations that are non-trivial. So, you know, a common rule of thumb is basically to look for in the correlation matrix to determine if you have correlations, at least several correlations that are above 0.30. And so as you're looking at this correlation matrix right here, you can see that we have some pretty good correlations. We've got a 0.44 here, 0.3398 there. We've got over here, we've got 0.7332, 0.705 right there. You know, so we've got multiple correlations in this matrix. There's a 0.72 over here. We've got multiple correlations in this matrix that at least indicates to us that it would be reasonable to carry out our factor analysis. So that's really kind of the first component of determining if it's reasonable. The next thing that we want to look at in addition is we want to look to see, do we have linear dependencies that would produce essentially singularity. And what singularity refers to is a situation where you have a linear dependency that will prevent certain matrix operations to be carried out, and you'll end up with a solution that's not going to work. You also have the issue of multicollinearity, where you have such high relationships in your correlation matrix that could also generate inadmissible estimates. So we don't want those issues to occur. So to check this out, what we will do is we will compute the determinant of our correlation matrix. So the determinant you can think of as a generalized variance for the correlation matrix, and we don't want the determinant to be 0. So we want it to be greater than 0. And there's a common sort of threshold that's given. Also, if you read through Watkins' book on exploratory factor analysis with Stata and some other places, you'll see that I guess you could say the threshold, if you will, that we're looking for is a determinant value that's going to be greater than 0.00001. So that's kind of what we're looking for there. So we need to actually compute the determinant of our matrix. So I'll show you the first way is just to, since we've run our correlation matrix, then we can kind of pivot off of the estimates in that matrix to generate the determinant. So I'll type in matrix R equals and then RC. So what's going to happen is that once we've generated this correlation matrix, that information is stored as a set of estimates, but we want to be able to access those contents and generate our determinant. So I'm typing in matrix R equals RC. Then I'm going to type in matrix D equals, and then we'll type in DET and then R. So essentially the second command is essentially computing the determinant of R and saving it into its own matrix. And then we can actually see the determinant if we type in matrix list D right here. So these are basically commands from Watkins' book that was shared. So this is a really nice addition right here. So what we'll do is we'll highlight these and we'll press the execute selection button, and you can see the determinant value right here. It's 0.10845. So as you can see, that value is clearly greater than the threshold of 0.00001. So in that case, we're not going to have any concerns about there being collinearity or singularity within our matrix. So the next step, another set of diagnostics that we can generate include not only the determinant, but also the Kaiser-Meyer-Olkin measure for assessing factorability of the matrix, as well as the Bartlett's test. And so in order to generate those results, we can use a package that has been written so what we'll do is we're going to type in SSC install factor test. Now, what the package that I'm talking about, this is a user written package. So the functions associated with this are not part of the base Stata program, but rather a user has written this package, and then we can use the commands with this package. It's kind of the same principle as if you're familiar with R. Basically, to use functions associated with a package, you have to actually have the package installed. So what we're doing is we're basically calling up this package from a website and then having it be installed, and then we can use the function associated with it. So I'm going to highlight this and click on execute selection, and the package has already been installed, of course, because I've already gone through this, but this just kind of shows you the steps right there. So then the next step is to use the function. So I'm going to type in factor test and then my variable names. So I'll type these in right here and then highlight all of this, and we'll click on execute selection. And you'll see that we get several pieces of information. We get our determinant again. So we technically didn't have to use those matrix operations to get it. But that was kind of showing you the steps right there. This is the determinant of the matrix, so the 0.108. We have Bartlett's test of sphericity, which is next. So basically, it's a chi-square test. This is it right here. And so what we're testing is whether our observed correlations, our correlation matrix, does it differ significantly from an identity matrix? So an identity matrix is one where you have ones along the principal diagonal and zeros on the off diagonal. And with an identity matrix, if our correlation matrix was an identity matrix, it would basically indicate that all our variables are uncorrelated with each other. So, and that's not an ideal situation, as we kind of talked about earlier when we were looking just to see if our correlation matrix had any correlations that were 0.3, at least 0.3. This is another way of kind of making that determination as to whether we have trivial correlations or there's enough there that it makes sense to carry out our factor analysis. So a statistically significant Bartlett's test would be regarded as an indication of that it's appropriate to carry out our analysis. Now, keep in mind too, though, that this test is going to be affected by sample size. And so, if you happen to have a very large sample size, you can have a situation where you have very trivial correlations, but the test be statistically significant. So it's really kind of good to look at both this test result and look at the actual correlations themselves to make that determination. But nevertheless, you can see that we have a significant Bartlett's test result, which would signal that we have a correlation matrix that where it makes sense to carry out the factor analysis. The last index that we have down here is the Kaiser-Meyer-Olkin measure of sampling adequacy. You'll see this referred to as the KMO measure. And so this is just another way that we can make a determination that it makes sense to carry out our factor analysis. So without getting into all the details, there are various rules of thumb for evaluating the factorability of a matrix using this index. And the most common system, I guess you could say, in terms of sort of labeling the factorability of our matrix is this system right here, where we have values that fall between 0 and 0.49, which suggests it's unacceptable to carry out the factor analysis. 0.50 to 0.59 is miserable. You've got 0.60 to 0.69 mediocre, 0.7 to 0.79 middling. 0.8 to 0.89 meritorious, and 0.9 to 1 marvelous. So these are just kind of labels that have been proposed by Kaiser in his earlier work during basically the 1960s and 70s. So at any rate, if we look at our KMO value in our output, you see that we have a KMO of 0.76, which according to this system would be considered middling, but this oftentimes is regarded as generally acceptable for carrying out the factor analysis. So at this point, we can say that, if we take all of our information up to this point, we can say that, okay, it looks like it's reasonable to carry out our exploratory factor analysis. So given that, now what we want to do is to determine how many factors might underlie or explain the correlations among our set of measured variables. And so this is the next part of our exploratory phase, which is making that determination with respect to the number of factors. So once we've made that determination, though, going through these steps, then the next step is to essentially kind of force that factor solution and interpret our results, which incorporate also the interpretation of rotated factor loadings. So in this process of exploring for the factor structure, there are a number of rules of thumb out there. A number of approaches out there, I should say. One common approach is to use the eigenvalue cutoff rule. So essentially, what that means is that you subject your data to a principal components analysis and extract a set of eigenvalues, which are essentially summarizing the variance among involving a set of measured variables, and basically retaining the number of factors that happen to have eigenvalues that are greater than 1. That's the old eigenvalue cutoff rule. Basically, the minimum eigenvalue for factor retention is 1, and that's also referred to as the Kaiser criterion. So that's one approach. It's not actually one of the better approaches to making a determination of the number of factors. It's actually regarded as nowadays it's not one of the approaches that's encouraged by factor analysts. Another approach is to examine a scree plot. So a scree plot basically provides visualization of the eigenvalues associated with the components from that principal components analysis. And the idea is that what we're doing is we're essentially screening our data to make that determination. So we're using principal components analysis in order to generate those eigenvalues, and then we can, from there, we can also visualize possible factors that are in our data. So in order to carry out our analysis, what we'll do, first off, in order to get our eigenvalues, what we'll do is we'll type in PCA. So we're going to use the PCA command and then type in our variables. Okay, so this is the first step right here. So I'm going to highlight this and run it. And just keep in mind that the eigenvalue cutoff rule was actually developed in the context with using PCA in order to identify the number of factors. So it's not really advisable, if you're going to use that rule, to utilize a common factor analytic technique in order to identify the number of factors, because it really developed in the context with PCA. So if we were going to use the eigenvalue cutoff rule, or at least kind of consider it in relation to other information, then in that particular case, we can look at our output, and you'll see that we've got, let me highlight it here. We've got over here, we've got a column containing eigenvalues, and we've got two of these components right here that have eigenvalues that are greater than 1. So if we were going to use the eigenvalue cutoff rule, then in that particular case, that would suggest a two-factor model. So that would be one piece of information right there that might suggest retaining two factors. The other option to use the scree plot, and we're also going to cover some other things as well here in terms of determining number of factors, but we can type in scree test right here, and at our scree plot, scree plot, and highlight, and we'll run it. So now you can see that we get this plot of eigenvalues against those component numbers. So as we're looking at this, just kind of notice that, it looks like the side of a mountain. All right. And so in terms of interpreting this scree plot, what we're looking at, in order to determine the number of factors, is we look at the main eigenvalues on the side of the mountain, so to speak, or as we're getting closer to the peak. And then we got those eigenvalues that look like they're at the base of a mountain. It's kind of the rubble, if you will. And so as you're looking at this, you can see that we've got two eigenvalues that are clearly on sort of the steeper parts of the mountain. We've got this eigenvalue right here for component 1, eigenvalue here for component 2, and you can then see that as we move from component 1 to 2 to 3, you can see the slopes are kind of leveling off. Then when we move to 3 to 4, it's not as steep as what we have between 2 and 3. Between 4 and 5, maybe a little bit more slope, but still not much change. And then from 5 to 6, not much change. So in a nutshell, what we're looking at is kind of, if you want to think about it too as kind of an arm, if you kind of hold, bend an arm or whatever, this might be considered the elbow, and you would retain the number of factors above the elbow. So in this case right here, the scree plot visual indication might suggest retaining a 2-factor solution as well, or retaining 2 factors as well. Now, I will say this too, that if you wanted to use a common factor analytic approach like iterated principal components or maximum likelihood and generate the scree plot from that, that would also be perfectly permissible. So you could use either of those approaches, but most commonly it's going to be that you're using the scree plot from that components analysis. So the next approach that we're going to take in terms of determining the number of factors is parallel analysis. So parallel analysis basically involves taking the eigenvalues that we've generated from our principal components solution and comparing those eigenvalues against randomly generated eigenvalues. And the idea is that we would retain the number of factors, or we would assume that the number of factors is related to the number of eigenvalues from our PCA that exceed the randomly generated eigenvalues. So in order to do that, what we're going to use is another user-written package called FAPARA. All right. Now, in order to get this, we're going to use the search function, and we're going to type in FAPARA. Okay, so we need to locate the package. So I'm going to use the search command right there, the name of the package right there, and then we'll run it. So now you can see that we get this box with information related to this package and so forth. I'm going to go down here. It says 1 package found. Stay down here, and I'm going to click on this. It says FAPARA from this website. So I'll click on this, and you'll see that there's a button that says, it says click here to install. And so I'll click on that to install that package. And if you want a little bit more detail in relation to that package, you can click on this little FAPARA.HLP. That's a help file right there. So I've installed the package, and so now we are ready to go in terms of carrying out our parallel analysis. And once you've installed the package, there's not going to be any need to reinstall it. So just kind of keep that in mind, unless maybe there's an update later on that you want to have. So at this point, we are going to use the command associated with this package, which will be FAPARA, comma, then we're going to type PCA, then reps, and reps is referring to the number of simulated data sets from which we're going to generate our random eigenvalues. So I'm going to type in 1000 right here. And then we can set a seed number. So if I type in seed and then a seed number, I'll just type in 1, 2, 3, 4, 5. If I wanted to go back and reproduce the same results with the randomly generated eigenvalues, that seed number is going to guarantee that I have the same randomly generated eigenvalues in the future associated with this. And so that can be useful. If you don't want to worry about that, if you don't mind if you run the analysis and then generate the random eigenvalues and then you rerun it and you get different values, if that's not something that concerns you, then there's no need to set a seed number. But that's the basic idea behind that. So at this point, we are pivoting off of that earlier PCA. So just kind of keep that in mind. So we ran that earlier PCA up here. We've got those eigenvalues stored, and so we want to pivot off of those eigenvalues. So that's why we've got this laid out in the following way. So I'm going to highlight all of this, and click on execute selection. And so you'll see that I get another scree plot, but an overlay with the randomly generated eigenvalues. So you'll see that that dotted line represents those randomly generated eigenvalues. We're essentially connecting them. And so as you can see, it crosses over just above the elbow that we had referred to previously. And so that would suggest then that we have that two factors may be accounting for the relationships among our variables. If you want the actual values themselves, you can look in this table over here, and you've got the eigenvalues from the initial PCA. Then you've got the randomly generated eigenvalues right here. So you'll see that the first randomly generated eigenvalue is 1.19 right here. The second one is 1.0996. Then you've got 1.02. And so what we're looking at in terms of our data over here, the eigenvalues from our data, we essentially retain retain the number of factors where the eigenvalues from our data over here exceed the eigenvalues from the PCA, parallel analysis. And so once you have an eigenvalue associated with the data that drops below the randomly generated eigenvalue, then you retain everything above that. So you'll see that both for our factor 1, factor 2, the eigenvalues from the data right here is greater than the eigenvalues from that are randomly generated. But then on that third factor down here, you can see it's actually less than. And so in that particular case, you would that would support a two-factor solution as well. So now we've looked at three different approaches for making a determination with respect to the number of factors. We've used the eigenvalue cutoff rule, we've used the scree plot, and now we've used parallel analysis. One other option too is the minimum average partial correlation. And so in order to use that particular index, that does require yet another package. So in order to obtain that package, we'll type in SSC install and then minnap right there. Okay, so we're going to install this other package from this SSC site. And let me just kind of highlight, go ahead and click on the execute the do file. And so now you can see it's installed. It had already been previously installed, but now it's installed yet again. And we're going to use the minnap command associated with this package. So we're going to type that in and the names of our variables. So now we've got those names that are included. We'll highlight this and click on execute selection. And so now we get these minimum average partial correlations from our components. And essentially what we want to do is to select the number of components that are associated with the smallest map value. So as we're looking at this, you can see that we have essentially a comparison between different models. We've got a model with basically one component, two components, three components, and so forth. And in terms of making the determination of the number of factors, what we'll do is we are going to look at these values in this column over here. And you can see the smallest value right here, the 0.10246, is associated with a component solution that has two components. So in that case, we would use that to make the determination that in terms of the number of factors that may account for those relationships among our variables, that we would stick with a two-factor solution. So at this point, we now have another piece of evidence that suggests that maybe a two-factor solution is warranted. Okay, there is yet one other approach that we could use, and that also would entail comparing different factor models. And so whereas everything that we've done up to this point, we've actually been using a principal components approach, using the eigenvalues from the principal components analysis. We've used the scree plot from our principal components analysis. We used the minimum average partial correlations associated with the principal components analysis. And another approach is to use a technique that involves making model comparisons using a common factor analysis approach. So just kind of keep in mind, there's a long-standing arguments and debates in the factor analysis literature about using principal components and treating solutions from that as factors. But everything that we've discussed up to this point really developed around principal components analysis. So if you want to also consider perhaps using a common factor analytic approach, that with principal components analysis, you're summarizing all of the variation in a set of measured variables, whereas common factor analysis basically is focused on breaking down the correlations among a set of measured variables. So that's kind of the way to think about it. So if you also want to look at perhaps an exploratory technique that would involve a common factor analytic technique, then one option would be to compare models with different factors or different possible factors against each other using a common factor analytic technique. So what we're going to use in this case is maximum likelihood estimation. We're going to carry out maximum likelihood factor analysis, and then we're going to generate information indices associated with different factor models, and then make a determination of the number of factors from that as well. So what I'm going to type in is I'm going to type in factor, then the names of the variables right here, comma, and then I'll type in ML. So this is going to generate a maximum likelihood factor analysis solution. Now, at this point, we're still in the process of determining how many factors we want to retain in our final solution. So at this point, we don't really want all of the additional factor analysis information. All we want to do is to really generate the indices for the model comparison. So I can basically suppress all of the factor analysis output for this process by typing in quietly. Okay, and so that's going to suppress the maximum likelihood output. So if I highlight this and I execute the selection, you can see that nothing shows up, and that's fine. And that's basically the reason why is because I typed in quietly. I'm basically suppressing that output so I don't get quite so much stuff going on. You're welcome to generate that if you want to, but right now that's really not of a primary concern. So then we'll use the estat post estimation command and type factors. So when I highlight this and execute, now you can see that we get output in the form of the Akaike's information criteria, the Bayesian information criteria. You can see, so that's basically these indices right here. You also see that we've got the log likelihoods for 3 models as well. So you can see that in our output, we've got 3 different factor solutions. We've got essentially a 1-factor model, a 2-factor model, and a 3-factor model that are being compared. And so what we're looking for in terms of AIC and BIC, we're looking for the lowest values. So the lowest values of AIC and BIC are associated with the factor model that we would select. Okay, now these don't always agree with each other, and so it's possible that in certain circumstances maybe you might have a couple of solutions that might be viable. But in the current case right here, you can see that the lowest values of AIC, both AIC and BIC, are associated with a 2-factor model. So in this case, now we yet have some additional support for using a 2-factor model when we run our main analysis. So as you can see, we've gone through all of these different possible ways of assessing or making that determination of the number of factors. And it really is kind of important to keep in mind, they won't all necessarily agree. Okay, so even though they all agreed as we went through this particular demonstration right here, they don't have to agree. They don't necessarily have to agree. And so sometimes, you can have a situation where perhaps some approaches suggest maybe like a 2-factor model. Others might suggest a 3-factor model. And so in that particular case, then when you run your primary analysis, you might consider running it, running a 2 and a 3-factor model, and then sort of look at the interpretability of those models, and then make sort of your final determination off of that. But in this particular case, like I said, we have a set of procedures that we've gone through, and really all of them supported the same conclusion of a 2-factor model. So at this point now, we are ready to go in terms of running our final model and interpreting the factors. So in order to carry out our analysis, what we're going to do is we're going to take the factors that we determined from this previous step, and we are going to force a solution with that number of factors. So what we'll do at this point is we're going to use factor analysis again, but a common factor analytic approach. And there are various approaches that are available in Stata. So you have iterated principal factors, which is also referred to as principal axis factoring. You have a non-iterated version. You also have maximum likelihood. So for this demonstration, I'm just going to be using the iterated principal factors. And to carry out this particular analysis, I'm going to type in, I'm going to type in factor, then the names of my variables right here. And then I'll type in a comma, and then IPF for iterated principal factors. Then I'm going to type factors, and inside parenthesis, I'll type a 2 right here. And I oftentimes utilize SPSS in various analyses, and also with in teaching and so forth. And so one of the things, if you are an SPSS user and you want to get essentially the same results, the model is going to fit exactly the same, but if you want some of the same results in terms of the proportion of variance accounted for and cumulative variance and so forth, then you can get that by typing in alt divisor right here. And if you're not an SPSS user, you can still use the alt divisor approach as well. So it doesn't really matter. But if you are an SPSS user and you wanted to do a comparison of results, you can type that in. Then finally, we'll type in CIT and then 25. That's just basically referring to the number of iterations during our extraction here. So at this point, and you'll notice that the line is kind of running over kind of that little, there's like a vertical line kind of in the middle of the page right here. If that bothers you, one thing that you can do is you can wrap the syntax around. Basically just kind of pick a point, a space in the syntax, and you can type in 3 forward slashes, and then move the remainder of the code to the next line. So essentially, it's just it's telling the program, telling Stata that the commands are moving on, are continuing on to the next line. So at this point, I'm going to highlight all of this, and we will go up here to execute selection. And so now we've got our iterated principal factors solution. So in looking at our output, you'll see that we've got, first off, we've got various eigenvalues. But remember, in terms of the retained factors right here, we are retaining the first 2 factors, because when we went through that previous step, we determined that a 2-factor model is the best representation of our data. So we're going to use factors 1 and 2 right here. So in terms of reporting, be sure that you report on the eigenvalues associated with that, in this case, our 2 factors. And you'll notice that we've got proportions right here and cumulative proportions. So the proportions are basically reflecting the proportion of variation accounted for in those measured variables by each of the individual factors. And then the cumulative proportion is the overall proportion of variance accounted for. So as we're looking at this, you can see that the first factor accounts for about 41.7% of the variation. The second one accounts for about 14.6% of the variation. And then cumulatively, they account for about 56.28% of the variation. So when you're reporting, you report on these, obviously. Now, at this point, these are eigenvalues and proportions of variance accounted for and so forth associated with an unrotated solution. So if you look down at the bottom here, you'll see we've got, it says factor loadings and unique variances down here. And you've got factor one, factor two. And so typically when we carry out our factor analysis, we don't only want to determine how many factors there are, but we want to give them meaning. We want to give them some type of name. We want to define them. And the way that we define them is by looking at their associations with the measured variables that we have subjected to factor analysis. So when you look at the factor loading matrix down below, these are correlations between each measured variables and the factors. And so those variables that are more highly correlated with a given factor, we would use those in making, in naming or labeling or describing that factor. Correlations that are lower on a given factor, we don't, are variables that correlate lower with a given factor, we don't use in that process of naming or describing that factor. Now, at this point, these are what are referred to as unrotated factor loadings, and typically, there are issues in terms of trying to kind of make sense out of things with unrotated loadings. So I'm not going to go into all the details on that, but I am just going to say that typically we don't interpret these loadings. Typically, what we do is we submit our results up to this point to a rotation. So essentially we are reorienting the relationships between the measured variables and the factors in factor space, and then that's going to help facilitate interpretation of those factors. So we're not going to interpret the factors using the unrotated loadings that you see down in this matrix here. We're going to perform a rotation in order to increase their interpretability. You also see too that we have this column right here that says uniqueness. So this is basically going to be the proportion of variation in each of our measured variables that is unaccounted for by the factor solution. So you could think about it as it's basically measurement error. So it's the variation that's not accounted for. And often, typically when we are reporting on our results, we don't actually just kind of report on the uniqueness. Mainly, we actually report on communality, which is the proportion of variation that is accounted by the factors. Now, the other thing to note too is as you're looking at the factor one and factor two, you'll notice that, with each measured variable right here, it has a loading on each factor. So in a nutshell, the communality is reflecting the combined influence of both factors in our model on that particular variable. So in a nutshell, the communalities are reflecting the proportion of variation accounted for not just by a single factor, but by both factors, because both of them are related to our measured variable. So I'm going to show you in a bit about how to generate communalities, but that's kind of a general breakdown of what's going on at this point. So now what we need to do is we want to submit our solution up to this point to rotation. We want to be able to rotate the factor loadings in order to interpret our factors. So there's two general classes of rotation that are utilized in factor analysis. There's one class is what's referred to as an orthogonal rotations. The other class is oblique rotations. So, and within those classes, there are different types of orthogonal rotations and oblique rotations. But orthogonal rotations essentially are designed to maintain the orthogonality of the factors that have been extracted. So when we carry out our factor analysis, when we up to this point, remember that we had factor one, we had factor two, and each of those factors accounted for a certain percentage of variation in our measured variables. And we could actually talk about the variance accounted for in a cumulative sense. And that's because each factor is uncorrelated with the other factors within the model. So what that basically means then is that we can add up the proportions of variance accounted for by each factor at this point. And so the basic idea when we carry out the factor analysis is that the first factor is going to account for the greatest proportion of variation in our measured variables. And the second factor is going to be extracted such that it's uncorrelated with the first factor, but then it accounts for the next largest proportion of variation. Then if we continue that process, each factor that's extracted is going to be orthogonal or uncorrelated with the previous factors, but also is going to account for the subsequent proportions of variation. So the eigenvalues and the proportion of variation accounted for generally is going to decrease as more factors are extracted. But remember that basically each factor is extracted to be orthogonal with the previous factors. So if we carry out an orthogonal rotation, it's going to maintain that that idea of uncorrelated factors. So all we're doing in that case is we're performing a rotation where the factors remain at 90-degree angles, basically. So at any rate, what we're going to do is we're going to use one of those orthogonal rotations. Probably the most commonly used orthogonal rotation is Varimax rotation. So at this point, I'm going to kind of go in here a little bit, and we're going to perform a Varimax rotation. I'm going to type in rotate, comma, Varimax. Then I'm going to type in Kaiser right here, and we'll go ahead and use the Alt divisor as well, just so that we can kind of get output that's comparable to what we would see in SPSS. So SPSS, by the way, by default uses Kaiser normalization, and so that's why I'm typing that in. But at any rate, what we'll do at this point is we're going to highlight this and we'll run. And so now when we look at our output, you'll see that we get the results from our rotated solution. So you'll see that in terms of the variance accounted for, these values right here, these are eigenvalues. So these are the eigenvalues associated with the rotated factors. And what happens following rotation with rotation is that the variance that's accounted for gets kind of spread out more evenly across our factors. So the variance that that's accounted for prior to rotation will generally look different from the variance that's accounted for after rotation. So these are the eigenvalues that you see right there. And in terms of the proportion of variance accounted for by the factors, we see that the first factor accounts for 36% of the variance. The second one accounts for about 20% of the variance. If you add those two together, basically you can see that combined, those factors account for about 56% of the variance. Then when we look at this matrix down here, you'll see that they're describing it as a pattern matrix. In the context of an orthogonal rotation, basically the pattern matrix and the structure matrix are the same. And I'll talk a little bit about the difference between a pattern matrix and a structure matrix more when we go into oblique rotation. But essentially what we do is, again, we look at the relationships between our measured variables and the factors. Now, typically what we do is we adopt a minimum loading criteria on a given factor to basically say that, if a measured variable correlates at that threshold or above with a given factor, then we use that variable to help in naming or describing or defining that particular factor. So as you're looking at this, there are various rules of thumb out there. The rule of thumb I typically use would be a factor loading of 0.40 or greater would be used as sort of basically the 0.4 is a minimum criteria, and that 0.4 is an absolute value. So because you can have factor loadings that are negative as well as positive, so we'll use the absolute value of that in defining our factors. Now, in our case right here, we don't have any negative loadings, but that's just kind of highlighting that little point right there. Other common criteria might be a 0.32 serving as the minimum loading, or sometimes even a 0.3 as a minimum loading, but we're going to stick with 0.4. So as we're looking at our pattern matrix right here, you can see that these measured variables, paragraph completion, sentence completion, and word meaning, all of these meet the loading criteria on factor one. So you can see that the remaining variables right here are really exhibiting low loadings. So what that means practically then is that we're going to assume, or we're going to treat factor one as being defined by these three measured variables. We're going to name our factor one using the ideas or the concepts that are being measured with those variables. So we have paragraph completion, sentence completion, and word meaning. So that would suggest to us then that factor one might be called verbal ability. And so if you remember earlier on when I was talking about those two-factor solutions, and we had verbal ability in there, that's where this is coming from. We're naming this factor based on those three very high loadings. And so in a nutshell, the remaining measured variables we just treat as really not contributing to that definition. So we're just kind of excluding those, at least from a conceptual standpoint, from our definition of that particular factor. Then if we look at factor two, we've got our these three variables right here: visual perception, cubes, and lozenges right there. All three of those meet the minimum loading criteria on factor two. And so unfortunately, there's not really much definition of cubes and lozenges, but that first variable right there, visual perception, we might treat all of these as representing something like spatial ability. Okay, so under the assumption that the variance that they share is really reflecting kind of a spatial ability factor. So, and then in terms of those other measured variables right here, those are loading very low on that particular factor. So the basic idea is that we would say then that really based on this examination of our loading matrix, that we would say that that the relationships among our paragraph completion, sentence completion, and word completion appears to be largely a function of a verbal ability factor as producing the correlations among those variables, and then the relationships among visual perception, cubes, and lozenges is largely reflecting a spatial ability factor. Now, obviously, in our correlation matrix, we also have the interrelations between those sets of variables, but in large part, the relationships among those subsets of variables appears to be related to these particular factors that we've just been talking about. So then the next thing I want to show you, though, is carrying out the factor analysis, or rerunning our analysis, but then using an oblique rotation. So a common oblique rotation is Promax rotation. And so what we'll do is go ahead and go back into our editor right here, and we'll type in rotate, comma, Promax, and there's a kind of a little parameter right here that establishes how much we are allowing our variables to be correlated with each other. So I'm actually going to stick with the number right here that's kind of the default actually in SPSS, which is 4, and I'll type in oblique. Then I'm going to type in Kaiser, and then we'll type in Alt Divisor right here. And actually, I'll remove that oblique, and we'll just stick with rotate, comma, Varimax, Kaiser, Alt Divisor here. So I'm going to highlight this and click on the execute selection. And so now, as we're looking at our results, you'll see that we've got we have eigenvalues associated with our rotated solution, but in this case, because we're carrying, oh, excuse me, that's the Varimax. I'm sorry. I need to rerun this using Promax. So let me actually, I will just copy this and I will paste it down here. And instead of using Varimax, we will type in Promax. All right. So we'll highlight this and execute the selection right here. And so now, looking at our results, you can see it down here. It just says we have, it says the variances for each of our factors, but you'll notice this statement right here. It says rotated factors are correlated. So what that basically means, though, is that we can't talk about each factor in terms of accounting for additive amounts of variation in our measured variables, because the factors are correlated with each other. So we can still refer to proportions of variance accounted for right here, I suppose, but basically, we can't really think about these proportions in an additive sense, because if we go back and we think about it, when we ran our analysis, when we ran our original analysis, the iterated principal axis or principal factors analysis, we accounted for a cumulative proportion of variation. When we use Varimax rotation, we were still accounting for the same proportion of variation, but we could break down that proportion of variation in the measured variables into variation that's accounted for distinctly or uniquely by each factor. When we use an oblique rotation, however, we're still ultimately accounting for the same overall proportion of variation, but now, because the factors are correlated, we can't assign that variation to factor 1 and factor 2 and treat the variance accounted for as additive. So that's something to kind of keep in mind when you're reporting on your results. So at any rate, the variance, basically the eigenvalue for factor 1 is 2.38. The eigenvalue for factor 2 is 1.426. Now, we have down below, we've got our loading matrix, and it's a pattern matrix down here. Now, unlike the matrix that we saw above, prior to rotation, where it said pattern matrix, and also with our Varimax rotation, this matrix now cannot be interpreted as zero order correlations between each measured variable and the factors. And the reason why is because the factors are correlated with each other. So each loading, it's probably better to think about them as more akin to standardized regression coefficients than zero order correlations between the measured variables and the factors, because the loadings themselves are reflecting a partialing of the, if I'm looking at the relationship between, let's say, visual perception and factor 1 right here, we're looking at that relationship while partialing out factor 2 from that association. So if we look at visual perception and factor 2, this coefficient right here reflects a partialing of factor 1 from the association between factor 2 and visual perception. So these are not correlations between each measured variable and the factors. These are more akin to standardized factor loadings, or standardized partial regression coefficients. So there's a lot to kind of keep in mind as you're going through all this. So we can still use our loading criteria in making our judgment, but we need to kind of keep that in mind in terms of what these loadings are actually capturing. So if we go and we look at, if we still use the 0.4 loading criteria, we still see these coefficients right here. All of these, our paragraph completion, sentence completion, word meaning variables, all of those meet the minimum loading criteria. And then these variables right here, visual perception, cubes, and lozenges, meet the minimum loading criteria as well. The other thing to kind of note too, as we're going through these matrices, is that they're not always going to necessarily be as clean and clear as what you see right here. Sometimes it will be the case where you'll have loadings, like you'll have a measured variable that meets the minimum loading criteria on multiple factors. In that particular case, what you have is a little bit more ambiguity in terms of making a determination about which factor that variable represents. Does it even make sense to include that variable in the naming or defining of the factors if it's related to both, if it meets the minimum loading criteria on both? So that's where things get a little bit more complicated. But in the current case right here, it's very, it's very clean and clear about which variables are related to those factors. So if you want to further kind of unpack the relationships between the variables and these factors, then you can also generate a structure matrix. And a structure matrix does contain the correlations, the zero order correlations between each of the measured variables and those latent factors. Now, it's not recommended that you use the structure matrix exclusively when you're naming or defining those factors, because it ignores the relationships between the factors and those measured variables. But you can use it as sort of a supplement when you are making this judgment about kind of the overall thematic content associated with a factor. So in order to generate a structure matrix, what we'll do is we'll use, as a post estimation command, we'll type in estat, and then we'll type in structure. And so this is a follow-up to our Promax rotation output and so forth. So we'll click on execute selection, and now we have a structure matrix. So these are the zero order correlations between each variable and the factors. So in this particular case right here, we see basically a similar pattern emerge in terms of the correlations here between our measured variables and those factors. But you can also see some of the other associations look a little bit larger in terms of those other variables in relation to in terms of the other factors. And that's basically because these are zero order correlations. So we're not partialing out relationships involving, we're not parceling out the other factor when we're looking at the relationship between a given measured variable and that particular factor. But again, you can kind of use this matrix as additional information to talk about the kind of the thematic content of a factor. I will tell you too that when I ran this analysis right here, I didn't specify that kappa parameter there. So to keep our results, again, kind of consistent with SPSS, I'm just going to type in Promax with a 4 inside the parenthesis there. And so when I run the analysis right here, you can see that basically the output is reflecting that particular specification. So there you go. The next piece that I want to show you is that if you want to generate correlations among the factors, there's another post estimation command as well, which is estat common. Okay, so when I highlight this and run it, then I end up with the correlation between those two factors, which is 0.3718. So that's something else that you are likely going to want to report when you're writing up your results involving your factor analysis, or at least following an oblique rotation. Now, the last thing I want to show you is how to generate communality. So by default, Stata does not generate communalities for your measured variables. And as I said earlier, communalities reflect the proportion of variation in our measured variables that's accounted for by the full set of our retained factors. So in order to generate those, you can use the following syntax right here. So again, I'm going to go into this book, and this syntax was also provided by Watkins in the book on a step-by-step guide to exploratory factor analysis with Stata. So I'm going to type in matrix, and then M, and then equals, and then I'll type in J1, comma, COLSOF, and then E psi with a capital P, by the way. Then, so you can see it's very easy to make a mistake in here. So we've got that. We have, we'll type that in right there. We'll type in a 1 right here, and then minus E, and then psi. So what's happening in this case is that essentially we're pulling matrix information out of some of our previous estimates, and then we are computing the communalities. So at this point, I can type in matrix list and M and highlight it, and we'll execute the selection. So now you can see we've got communalities associated with each of our measured variables right here. So I will tell you that, under the video description, I do have a PowerPoint, and I'll also include, just an example do file, so you can kind of study up on this syntax a little bit more closely. But that's going to basically wrap up this video discussion. I know it's a lot to kind of go through, but as you can see, factor analysis is not something that is, where you can just kind of click a few buttons and understand what you're doing. It does require thinking through this strategically. And also, as I kind of went through this whole process, I wanted to make sure that to kind of show you or model to you kind of a general strategy for setting up a do file that you could use not only for the current analysis, but perhaps you could save it and use it for other analyses just by kind of switching out the variable names and so forth. So at any rate, that's going to conclude this video, and I really appreciate you watching.